Today's objective is simplifying square roots. So just like you can simplify fractions, 3/6 is the same as 1/2 because you can divide a 3 out of both the 3 and the 6 to get 1/2. You can simplify square roots by finding the perfect square factors and taking their square root. This is like a puzzle. But remember, sometimes puzzles are a little bit frustrating at the beginning, but then once you get the hang of it, they're fun. Okay, so don't get frustrated because this ends up being fun. So let's review perfect squares, and I'd like you to write this down. And I'm beginning with 12 squared, and I think you can write it down as we go along because I'd like you to see all of the things I want to talk about to help you remember. 12 squared is 144. You know that, and I'll talk about that and underlined in a little bit. 13 squared is 169, and you can help remember because the numbers go 3, 6, 9 in order. Okay? 14 squared is 196. The 6, 9 is now reversed, 9, 6. 15 squared is 225. It's the only one really this small that ends in a 5 because 25 squared ends in a 5 also. 16 squared is 256. 17 squared is 289, and it goes 7, 8, 9. And it's getting bigger. It's almost 20, so you know that it's not going to be 100. So it's 7, 8, 9. Maybe you can remember 1, 2, and then 7, 8, 9. 18 squared is something I never remember, but it's 324. Maybe you could say 8 times 3 is 24. That's pretty good, right? But I still wouldn't remember that. 19 squared is 361, and with the 9, there's a 3 and 6, like counting by threes, but I don't remember that one very well either. But 20 squared is 400, and I remember that because 2 times 2 is 4, and then I add 2 zeros. 21 squared is 441, and this one's cool because if you reverse the order of 21, what do you get? 12. And if you reverse the order of 441, what do you get? 144. That's pretty cool, huh? All right, 22 squared is 484. So we have the 2, we double it, and then we go back down. 23 squared is 529. I never remember that one. But these next ones are pretty neat. 25 squared is 625. That's also the same as 5 to the 3rd power, okay? So I'll write that it's also 5 to the 3rd because it's 5 times 5, which is 25, times 5, which is 125, times 5. 5 times 5 times 5. Oops, it's 5 to the 4th, silly. 5 to the 4th because it's 5 times 5, 25, times 5 times 5, 25. But it ends in a 5 also because 5 times 5 will end in a 5. 24 squared and 26 squared are 100 apart. So 24 squared is 576 and 26 squared is 626. Now you don't need to memorize all of these, but if you can memorize some, it will be helpful too. All right, now let's get to the simplifying. The reason I want you to know the perfect squares is because you need to know the perfect squares that are inside of your square roots. I want you, 48 has a lot of factors. You could say 1 times 48, 2 times 24. We're going to do 3 times 16. You could also do 4 times 12 or 6 times 8. But I need you to think of the perfect square factor. So it needs to have the 16 in it. So we can break down our factors under the radical sign, say 3 times 16. And then we can write them separately. Square root of 3 times the square root of 16. Those are like terms. And then I can say, oh my gosh, the square root of 16 is 4. So it's the square root of 3 times 4, but we don't write it this way with a dot in the middle. We put the perfect square on the outside so that it's kind of the same as writing 2x. We just say 4 times the square root of 3, or 4 root 3. Okay, that's when you're in 10th grade. Let's do the square root of 18. Don't tell me 3 times 6. Tell me 2 times 9. So notice I've skipped a couple of steps. Here I showed everything, but it doesn't need to be that long, so I want to show you. The square root of 18 is the same as the square root of 2 times the square root of 9, because 9 is the perfect square. The square root of 9 is 3. It goes in the front. I could have written 9 times 2. I don't know why I just wrote the smaller number first. The square root of 9 is 3, and then the square root of 2 is not a perfect square, so it's just 3 times the square root of 2. How about the square root of 98? Whenever you have a big number like this that you don't know, divide it by 2, because often all I've done is multiply it by 2 or the book. So the square root of 98 is the square root of 2 times the square root of 49. The square root of 49 is 7. So the square root of 98 is 7 times the square root of 2, because we can't get rid of the non-perfect squares. So the puzzle part is finding the perfect square and pulling it out. What if it looks like a fraction? The square root of 3 over the square root of 3/16. Well, you can rewrite the numerator and denominator separately also. The square root of 3 over the square root of 16. The square root of 3 cannot be simplified, but the square root of 16 is 4. How about the square root of 16 divided by 25? Separate it out, the square root of 16 over the square root of 25. This is an important step that you must do, okay? The square root of 16 is 4, the square root of 25 is 5. Because when you're simplifying, if you can't simplify it, the radical needs to be around that number. And if you just left it like this, you might leave it as the square root of 3 over 4, and then you might go, oh, 4 is a perfect square, and then kill me 2, and you'd mess up. So you write it separately, take the square root. There's nothing you can do with that 4, it's just a 4, okay? How about the square root of 32 over 50? Well, the square root of 32 could be written as the square root of 2 times 16, and the square root of 50 can be written as 2 times 25. Now you need to remember, anything over itself is 1. So the square root of 2 over the square root of 2 is 1. So we end up with the square root of 16 over the square root of 25, just like we had here. So it's 4/5. Another way to do this problem is to simplify the fraction inside of the radical. So we could have said the square root of 32 over 50 is reduced. It's the same as the square root of 16 over 25. You can reduce a fraction inside a radical just like you could reduce a regular fraction, but it's still inside the radical, okay? And sometimes you won't be able to take the perfect square of both of them. All right, and this year, all of the denominators will be perfect squares. Not next year, but this year they will be. All right, let's add in some variables. Oh boy. So here's our problem we're going to do, and then we're going to talk a little bit, and then we'll go do the problems. So the square root of 16 times x squared can be broken down to be the square root of 16 and the square root of x squared. Well, you know the square root of 16 is 4, but let's talk about why the square root of x squared is x. Any even exponent is a perfect square. 2, 4, 6, 8. Because with exponent multiplication, we add the exponents. Remember, if I had a to the 3rd power times a to the 3rd power, you would tell me that's a to the 6th power, because this means there are 3 a's here, plus 3 more a's is 6 a's. But instead of writing it all out, we realized we could just add the exponents. X squared times x squared, x to the 4th. And y times y is y squared, because really there are 2 invisible 1's here, right? So to undo this problem, the square root of a to the 6th is half of that, a to the 3rd, because in order to get it, we just added itself. The square root of x to the 4th is x squared, because in order to get x to the 4th, we just added the exponents. The square root of y squared is y, because in order to get the y squared, we just added the 1's. So to get the square root of an even exponent, we just divide by 2. That kind of looks like a 6, doesn't it? I'll put a red over here. Divide by 2. Because dividing by 2, that's the same as whatever our number was when we added it to ourselves, we basically times it by 2. All right, an odd exponent takes one more step. If you have x to the 5th, we know that that's the same as x to the 4th times x. You just take the even number that's below it. X to the 4th, the square root of x to the 4th, divide your exponent by 2 is x squared, and the square root of just 1x stays the square root of just 1x. you always have the square root of x left over because you use the perfect square of the even number below your odd number. So this is the part that's a little bit frustrating at first because it's totally new, because it's not numbers, but you can do it. I just want you to think about it. So the square root of y to the 7th is the same as the square root of y to the 6th times the square root of y. What's the square root of y to the 6th? What times itself will be y to the 6th? Y to the 3rd times the square root of y. Let's do these two and then we'll go up and finish those, okay? The square root of x squared and y to the 3rd is the same as the square root of x squared, y squared, y. So when I do these, I don't just write x squared and y to the 3rd, I break it down in my first step to the perfect square and what's left over. Square root of x squared is x, the square root of y squared is y, and then so we still have the square root of y. So it's xy times the square root of y. How about x to the 7th, the square root of x to the 7th, y to the 9th? Well, what's the perfect square closest to this? 1 less. 6 plus 1 is 7. 1 less of our 9 and our leftover. The square root of x to the 6th, the square root of y to the 8th, and then put these two back together. So I could have done each step individually and then rearranged it, but I'm going to take my perfect squares first and put them together. We don't do a whole lot of this, but there's a little bit. All right, so back here, the square root of 16x squared, the square root of 16 is 4. What's the square root of x squared? Hopefully you said x. How about 50, the square root of 50, y to the 4th? Well, the square root of 50 is the same as the square root of 2 times the square root of 25, and the square root of y to the 4th is a perfect square because it's an even exponent. So we end up with the square root of 25 is 5. The square root of y to the 4th is y squared times the square root of 2. All right, one more. Square root of 32, x squared, y squared, z to the 3rd. What's 32? Am I going to say 8 times 4? 4 is a perfect square. Oh, but in 8, that's 2 times 4. So I want the biggest perfect square. So I'm going to say the square root of 16 times the square root of 2 times x squared, y squared. Oh, I'm running out of room. Z squared, z. Don't those look like 2's? That's why I always cross them. All right. It's hard to write like this, as you can tell. I don't do a very good job. Square root of 16 is 4. I'm done with that. I'm going to cross it out so I know because I have so many here. The square root of x squared is x. The square root of y squared is y. The square root of z squared is z. Any perfect squares left over? Nope. So put your non-perfect squares back together. So the square root of 32x squared y squared z to the 3rd is 4xyz times the square root of 2z. Or, to be cool, 4xyz root 2z. And that's it.